Okay, so yeah, so hello everyone. Welcome to the week 8 of problem solving session for the discrete mathematics course. And last time we saw some uh, definitions about graphs and their properties and so on. And today we will dive more into graphs. So yeah, so today's content is also going to be about graphs. And yeah, we'll look into the examples, and if and when we need the definitions we will define them. Okay, so last time there was this question that we could not do because of lack of time. So we will start with that, and we'll finish it off, and then we'll move on to the questions for this week. So what you're given is you are given this graph which has um, yeah, hi Akansha. So you're given this graph which has 5 vertices, and you want to find the total number of spanning subgraphs. So what do you mean by spanning subgraph? So spanning just means that it's a um, it contains all vertices in G. And what do you mean by subgraph? Subgraph is just a subset of edges and vertices of a graph. So it's a so for example, A E C here is a subgraph, and if I add this one more edge, that is also a subgraph. So essentially you are just deleting either some vertices or some edges or both. So that's what a subgraph is. So okay, so the question is, how many spanning subgraphs are there? So okay, so O just says 32. Why do you think so?
Ma'am, because I think there are subgraphs are we can assume the graph as a set and related to subsets of the graph, and then we can find out like 2 to the n. There are 5 vertices, so 2 to the 5, 32.
Okay. Um, okay. So let's understand. Okay. So the answer is correct, but I think that is a it's a coincidence that you have 5 vertices and 5 edges here. So for example, if I have one sorry, um, yeah. So for example, if I add one more edge like this, then yeah, then according to that justification, the number of subgraphs would still remain the same, right? Because the vertices hasn't changed, so the answer according to that would still be 32. But notice that you have one more edge here, right? So you can still play around with that edge and get more and more subgraphs. So um, okay, so in this case you have this 5 edges. Okay, so assume for now that you don't have this additional. Okay, so assume for now that you don't have this additional edge, and uh, what you do is you have this 1 2 3 4 5 edges, and for each of the yeah, for each of the edge you have a choice of whether that edge should be there or not. So this could be there, then again for this edge 3 it may or may not be there, so I'm choosing to not take 2, and then I'm just choosing this. So this gives me one spanning subgraph, and this also is a spanning subgraph. So B C A D E, and let's say I just draw B to C. This is also a spanning subgraph because we never insisted that the graph should be connected. So it's possible that you have all the vertices and they are disconnected. So in fact, if you don't even have this edge, that is still a spanning subgraph. So what you are basically doing is you are just asking at every point whether a particular edge is to be included in the graph or not. So for every edge, you have two choices: either include it in the subgraph or exclude. So yeah, so in this case there are 5 vertices, so for each of them you have two choices, so that would be 2 into 2 into 2 into this. So therefore you get 32 possible spanning subgraphs. But yeah, but the difference between vertices and edges, is that clear? So I mean, so if I add this one more edge, then additionally you get more subgraphs, right? Now you have choices for every subgraph that you have. So let's say this was your g1, g2, or say h1, h2, and so on up to h32. These are the 32 possible spanning subgraphs for the initial diagram. But now we are adding this one more edge. Now um, for each h1 here, you have two choices whether to include the edge DE or exclude it. So this happens for everyone. So therefore you get 32 plus 32, which is 64 choices if this were also an edge in the graph. So is this okay? Okay, good. So we can move on to the content of this week. So I think last time we already talked about this adjacency matrix and incidence matrix. So just to quickly recall, in adjacency matrix you have an n cross n matrix where n is the number of vertices, and let's say they are labeled 1 to n, and the entry of the matrix is 0 if there is no edge from 1 to e, and 1 if there is an edge from uh, between the two vertices. So yeah, that is your adjacency matrix. And what is incidence matrix? Incidence matrix is that you have vertices on this side, so these are labeled by vertices and the columns are labeled by edges, and you, for vertex I and edge j, you write 1 if and only if the vertex I is incident on edge j. Okay, so you're given this graph and you want to write two representations of it. One is the adjacency matrix form, the other is the incidence matrix form. So let's try this. You have A, B, C, D, E. Okay, so can you tell me the entries? This is the incidence matrix.
Yes, ma'am.
Sorry.
Incidence or
Sorry,
adjacency?
sorry, sorry. Yeah, adjacency matrix. Yeah.
In the diagonal, we can write zeros like A,
Okay.
A, B, B,
Yeah.
C, C.
Yeah.
And in the row of A,
Hmm.
we can write 1 in C and E column and
Hmm.
others 0.
Hmm.
In B, C and D 1, others 0.
Yeah.
In C, A and B 1 and others 0. In D, B and E 1 and others 0.
Okay.
And in E, A and D 1, others 0.
Okay. Good. So in fact this is a cycle, right? So if you just pull this graph, it's a cycle of length 5. That's why for every um, yeah, for every vertex here you have I mean, it's connected to two other vertices. It's a degree two regular graph. And let's say Okay. So, do you observe anything about this matrix? Is there any property that you can see? Um,
Ma'am, is it symmetric?
exactly, it is symmetric. So, this is symmetric because uh, if if A is connected to C, then C is also connected to A. That's why if say A to C is 1, then uh, CA is also 1. But if I add directions to it, so if I say that, I mean, say if I have something like this, then how do the values change? So, for example, um, A to E, this would be 1 because A is connected to, I mean, there is an edge that goes from A to E, but E to A, this would be 0 because there is no edge that takes you from E to A. So that will no longer be symmetric. But yeah, for our case, let's assume that we do not have directions, and um, let's try to write the incidence matrix for this. So maybe I'll make some space here. Yeah, just give me a minute. So you have A, B, C, D, E, and maybe I'll call these edges as 1, 2, 3, 4, 5. So we have, okay. So what are the values for this? Okay, so this vertex A, this is incident on the edge 2 and it is incident on the edge 4, right? So for 2 and 4 I'm going to write 1, but for the rest of them I'm going to write a 0. Similarly, let's look at B. So what are the two edges that B is incident on?
1 and 3.
1 and 3, right? So for B you will write 1 and 3 and the rest of them are zeros. Then for C,
1 and 2.
D,
3 and 5.
3 and 5.
And E, 4 and 5.
E, 4 and 5, right? So yeah, in this case, right, it does not make sense for this matrix to be symmetric. I mean, because yeah, because I mean, on this side you have vertices and on this side you have edges. So um, yeah. So for example, A is incident on 3 does not mean that C should be incident on 1. Those are completely unrelated quantities. Therefore, it does not make sense to say that the matrix is symmetric or not. Is that clear? Okay, good. So yeah. So what let's define, there's a special kind of graph called bipartite graph, and it turns out that so this graph theory is a huge area in itself, and one reason why we are interested in graphs is because it's easy to model some real life situations in terms of graphs and then study the properties about them to conclude something. So for example, if you've done this theory of computation course, you must have seen how we use the graphs to model the DFAs, automata, and so on. And these are not the only place where graphs is used, but in case you have done the course or you have seen this, then I mean, I'm just connecting. If and if you don't know, then it's okay. Don't yeah, it's fine. So yeah, so one very special kind of graphs that lies out there is what is called a bipartite graph, and the reason it is interesting is that for a lot of cases, it's if you want to say some property holds for a graph, it's nice to check if it holds for the bipartite graph in the first place. And if it holds, then you can go on and try to see if it is true for the graphs. But there is a huge research that goes on in the area of bipartite graphs itself. So I mean, just want to mention. So what do you mean by bipartite graph? So given a graph GVE, if you can partition the vertices into two sets, so let's say V1 and V2. So these are the sets of vertices that you had, and you have these two partitions V1 and V2, which I'm just drawing here. And now you draw the edges across them. So what happens is, if you can just if you look at any edge in the graph, those edges just go from V1 to V2 or V2 to V1 in case it is directed. But it cannot be that there is a vertex here and there is a vertex here and they are connected by an edge. So all the edges would look like this. Therefore it's called bipartite. Similarly, you can define tripartite graphs and so on, but for now let's just deal with the bipartite graphs. So is the definition clear? It's basically that you can partition the vertex set into V1 V2 such that all the edges, if you look at the edges, they'll always be crossing from one set to the other. So the question is the graph that is given to you, is it bipartite? Okay, good. So how do you see that? You let's say you just start with vertex B, put it into partition V1, and try to draw all the edges that you have. So since it's a bipartite graph, you can't have edges within the set, so all the neighbors of B will have to be in the other set. So you put C here, then you put D here, and you put A here. Now you try to draw the edges on C. So C has an edge with A. So which is clearly not possible. So yeah, so that immediately tells you that the graph is not bipartite. Now okay, so do you observe what happened here? Do you see some like if something is true, then the graph is not bipartite, which happens in this case. So in this example, we drew this three edges and then we saw that C2A is an edge. So I mean, is there any property that you see which immediately tells you that okay, right? Yeah, so Akansha says that if there is a knot cycle in the graph, then it implies that graph is not bipartite. So why is that? You can try to formally prove this. The proof is not very hard. So let's say there is a knot cycle and assume it starts at this set A. Then all the edges that yeah, that are there. So if you traverse one edge, then okay, just yeah, yeah. So if you yeah, if you traverse one edge, then you always reach the other part. So but if you traverse two edges, then you always reach the first part. So if you and similarly on walking three edges, you will go to the other part. So essentially, if you take odd number of edges, then you always land up in the I'll call it set B for now because you're starting at A. Then you will always end up in set B. And similarly, if you take, this is an if and only if condition, because if you take even number of edges, you will always end up in A. So for example here, and so on. So if you take 2, 4, 6 and so on edges, you will always end up in the set A. Okay, so now the problem is that let's say you started at A, then you took some odd number of edges, and now you are here. So you say a cycle is odd if there are odd number of edges, right? So on traversing odd edges, you can never reach back to the position where you started. Your goal is to reach back here, but this is your starting vertex, so I'll call it S, but you can't reach there because you're taking odd number of edges. So yeah, so by the way, can there be then, I mean, is it possible that you have an even cycle? Okay, and Otis, what do you think? Yeah, good. So why is that? You can see a simple example for this, which is this. So if you just pull this out, this is nothing but a cycle of length 4. So okay, maybe uh, I'll not answer this, but I'll just pose a question to you. So is this I mean, what do you say, like, is this an if and only if statement, or is it true that it's just, I mean, it's just a one direction statement? What do you think? Is the question clear? Okay, so I think okay, so the same argument actually holds for the other direction as well. So um if your graph is bipartite, then you can't have an odd cycle. I mean, it's essentially, sorry, wait, um okay, so what I'm trying to say is it true that if the graph is not bipartite, then there is an odd cycle? And do you think is that does not exist? Yeah. So okay, so it turns out that this direction is also true, but it's not very trivial to show this. But okay, anyway, I'll not get into it, but you can try this out. The other direction also is in fact true. It's a characterization of a bipartite graph. Okay. But yeah, I hope at least I hope the question that we wanted to look at, um, I hope that is clear. Okay, good. So yeah, here is the next question. So you say that a graph G um, is self complementary if when you take the complement of it. Okay, so what do we mean by complement is just that you look at a graph G that is given to you, and if there is an edge, so there is an edge E in G complement if and only if E is not an edge in the G. So whatever is there in G will not be an edge in the complementary graph, and whatever is not an edge in the complement in the G will be an edge in the complementary graph. So the question is, you want to tell which of the following statements are true about the complementary graphs. I hope the definition makes sense. If not, then please let me know. um, okay, so let's look at the answer. So let's look at the statement by statement. So the first one um, is that you look at a vertex V in G, and you look at the degree of it, and then you look at the degree of the vertex in the complementary graph, and it says that the sum of this should always be equal to n. So let's say V is one vertex, and then you have n minus 1 other vertices in the graph because it's an n vertex graph. So let's say V has edges with k of them. Then yeah, maybe I'll just write here. Then in the complementary graph, exactly, G will only have this black edges because whatever is red is not going to be in the graph, and whatever is not there is going to be in the complementary graph. So black edges are the ones in G complement, and red ones are the ones in edges in G. So if you sum them up, you will exactly get n minus 1. So the first one is indeed true. So degree of V plus degree of this should indeed be equal to n minus 1. So statement 1 is true. Now, why do you think statement 2 is true?
Ma'am, it
Mm-hmm.
is said that it is a isomorphic graph, means both are isomorphic,
Hmm.
so their degree must be equal. Means uh,
Okay.
whichever vertices they have, their degree must be equal. So when we do subtraction, it will become zero.
Okay. Um, okay. So, um, I mean, the idea is correct, but it's not completely right to say that, because when you say isomorphism, it does not, uh, yeah, it does not mean that the same vertex is going to be mapped to the same vertex. So, for example, I have this graph. Um, I'll call these vertices 1, 2, 3, 4. What will be the complement of this? Can you tell me what are the edges that should be there?
Ma'am, one joining three,
Hmm.
two joining four, and one joining four.
Yeah, that is correct. So, do you think G and G complement are isomorphic?
Yes, ma'am.
Yeah. So why is that? Because you can isomorphism says that you can map vertices, you can relabel the vertices. So I'll relabel one with 1 in the graph G with 3, then I'll relabel 3 with 1, 2 with 4, and 4 with 2. Is that making sense? So this will be relabeled as 3, this will be relabeled as 1, this will be relabeled as 2, and this will be relabeled as 4. Then this is exactly the same graph and the same labels that you have. Is that uh, making sense? Yeah. So the thing is, but notice that you can't map 1 with 1 itself, because if you do, then look at the degree of 1 here. So the degree of 1 in the first graph is 1, but the degree of 1 in the second graph is 2. So it is not that degree of 1 in G is equal to degree of 1 in G bar, but the graphs are still isomorphic because there is a certain relabeling of vertices. I can just change the labels so that the graph becomes the same. So this is the isomorphism. So yeah, so G is a self complementary connected graph, but you have a vertex like this, so therefore statement 2 is not true. Is this okay? Okay, good. And what about statement 3? Do you think G bar is also self complementary?
Oh, yes, ma'am.
Exactly. So it just follows from the definition. So if you yeah, if you look at G, then what you've done is that E is present in the complement if and only if E is not there in the original graph. And now you're taking the complement of G itself. So now what you get is E is there in G bar if and only if E is not there in E of G complement, which is nothing but the same graph. This is same as E of G. Therefore, this is also self complementary. So 3 is true. What about the statement 4? So is it true that G bar is disconnected?
No, ma'am. It is false.
Right. So uh, this is a clear counter example. The same example that we used. Here you have that G is connected. You looked at its complementary graph, and it is still connected. So yeah. So what you have is 1 is true, and statement 1 is true, statement 3 is true, and the other are false, and we have counter examples for them. So your answer is B. Okay. Yeah, are there any questions about this, or shall we move on to the next one? Okay. um, right. So now you have to you've been given a set of graphs, so you have 4 graphs here. You want to tell which of them are Eulerian. So what do you mean by Eulerian? You say a graph is Eulerian if there is a circuit that um, starts at um, starts and ends at the same vertex, and visits each edge in G exactly once. So this exactly is a keyword here, because you're not allowed to repeat the edges, and you're also not allowed to leave out some edge. So this is what your Eulerian graph would mean. So for example, if I give you a graph like this, then yeah, then you have a simple path, a simple tool like this, which starts at this vertex, ends at this vertex, and visits every edge exactly once. But if I add, for example, okay, maybe I'll take a simpler example. So yeah, this is, let's say, the original graph you started with, and the Eulerian circuit for this is clear. But if I add one more edge, then it's not clear why you should have a tour, because if you start here and hmm, yeah, okay, if you start here and take all these edges, then notice that you have covered all the edges, but you have not reached at the same point. So you started here and you're ending here, so this is not allowed. You want to start at the same point and end at the same point. So in this case, it so happens that you, no matter how you try to use the edges, you will never end up in the same point where you started. So this does not have, and I mean, this is not an Eulerian graph in that sense. Okay, so similarly, what you can try out these examples, and you can let me know which of these do you think are Eulerian.
Ma'am, I think option A is Eulerian graph.
Right. So right, that is correct. So yeah. So what you might have done is you use this nice theorem that a graph is Eulerian if and only if every vertex in G has even degree. So this is a very nice characterization of um, finding out whether there is an Eulerian circuit or not. If you do not know such a theorem and you try to do a brute force sort of thing, then you'll have to look through all the possible um, tools that are there, so which could be exponential. So therefore this is a very nice theorem which just tells you in one shot whether the graph is Eulerian or not. So yeah, in this case, the degree of B is 4, the degree of C is 2, and so on. So for every vertex you have an even degree. Therefore this graph is Eulerian. But here, for example, B has a odd degree, so yeah, so you have a bad vertex right there. Similarly, here A is a bad vertex because it has a odd degree, and here again B is a bad vertex. So yeah, so B is not B, C, and D. Um, None of them are Eulerian. Now, yeah. So is um, any of you aware of this complexity classes called P and P? Okay, and Akansha, Snehal, what about you? Okay, so I'll just okay, so maybe I'll just not go into it, but I'll just mention that. So in general, what happens is you deal with what are called decision problems. What do I mean by decision problems? So you're given some input, you're you're given some input which could be a graph in this case, and your output is Yes, if it has some property. So in this case, let me call this if G has Euler, or if G is Eulerian, and you say no otherwise. Okay, so this is the problem that you have. This is similar to you, suppose I give you a number and I ask you to tell whether it's prime or not. In this case, the input instance is a graph and you want to check some other property. So the question is, how fast can you do this? So ideally, I would like to run in, let's say I have n vertices, I have m edges, then I would like to run in some polynomial time. So I would something like this, or even something like a huge number here is still good enough for me, but I don't want to, for example, go exponential in time. So this is bad. So what we are interested in is how efficient algorithms can be found. So based on that, there are classes like that. So you have a class of problems called P, which have efficient algorithms for which you can solve in polynomial time. And then there are problems that are hard. So it's okay if I mean you don't know this class and all, but so now there are problems here which you know are hard, or I mean which you don't know are hard, but you don't know an easy solution also. So um, it's open in that sense. So I mean, even if this does not make sense, I'll just ask you one thing. So if I give you this problem, then how fast can you tell whether the graph is Eulerian or not? So what would the algorithm look like?
Can discuss more calculated topics.
um yeah, actually I couldn't hear you.
Okay.
Okay. um Yeah, so Akansha says that what you do is you just go through each of the vertex in the graph. So your graph is given, and just like what we did here, you first check the degree of the vertex A, B, C, D, and so on. If at some point you get an odd degree vertex, then you say that no, the graph is not Eulerian. And at the end, if you have checked for all vertices, all of them have even degree, then you declare that the graph is Eulerian. So what you're saying is the algorithm is simply that check for degree of all vertices. If there is odd degree vertex, then return no, otherwise say yes at the end. So what is like running time of this algorithm? You just checking whether checking for the degree of vertex is an order n time operation, because if I give you adjacency matrix, you will just sum up the rows, right? So if you sum up the rows in the values in the row, then you get the degree of the graph. And if I give you incidence matrix, it's still the same. So yeah, so there are only n vertices. For each of them you are doing order n many operations. So you're essentially doing this in polynomial time, which is good enough, which is you can try to reduce this, but this is a good enough algorithm for us. So I'll yeah, so right now we know that this Eulerian checking has a polynomial time solution, but very soon I'll tell you about some problems here which look very similar to this, but you don't know an algorithm which is easy. So I mean, will yeah, I think this is, yeah, I'll mention it at the end of this problem. So similar to Eulerian graphs, you also have what are called Hamiltonian graphs. So what do you mean by Hamiltonian graphs? Is that there is a cycle, or there is a circuit that starts and ends at the same vertex, and traverses each vertex exactly once. So the only difference between the definition of the Eulerian graph and Hamiltonian graph is that you are looking at vertex here, and earlier you were looking at edges. So in Hamiltonian, okay, yeah. So for example, this is a Hamiltonian. This red thing that I've drawn here is a Hamiltonian circuit, because I have a um, I have a circuit which starts at the same vertex, ends at the same vertex, um, and includes all the vertices. So that's about the definition. Now you have three statements, and you want to tell which of them are true or not. So I'll uh, I'll let you think about this for a couple of minutes. Okay, so what do you think about statement one? So if a graph has an Eulerian tool, then is it necessary that it has a Hamiltonian tool? I mean Hamiltonian uh, circuit. Okay, one counter example. Yeah. Um, yeah. Sorry, I think there was some sound in the background, so I couldn't hear you. Um, okay. So Akansha.
Sorry. I was saying no.
Oh, okay.
Maybe.
So yeah. So Akansha, why do you think it's false? Do you have a counter example?
Ma'am, the graph which looks like a bow tie, that is Eulerian, but it is not Hamiltonian because the middle vertex, it will be have to be visited twice.
Exactly. So that is correct. So in fact, you can generalize on this, and you can say that you take any two cycles and connect them, like connect one vertex with them together. So what you're saying is exactly right. So if you, no matter how you traverse this, you will have to visit this vertex um, multiple times. So this has a Hamiltonian cycle, which is that you go this way. So you started and ended at the same vertex, but but yeah, you do not have Eulerian. Sorry, this is the opposite. So this is, you have Eulerian but you do not have, but not Hamiltonian. So 1 is not true. What about 2? False. Right. So I think this example would also work, where if you look at this, okay, maybe I'll draw it. If you go like this, or sorry, go like this, then you have visited every vertex exactly once, and you have started and reached at the same vertex. So this is a Hamiltonian, this graph is Hamiltonian, but you cannot cover this edge and still reach at the same vertex, because if you take this edge now, then you will reach here whereas you started here. Or an easy way to see that is, again, use the theorem, there is an odd degree vertex. So since there is an odd degree vertex, you can never get an Eulerian too. So this is Hamiltonian but not Eulerian. Yeah, and what about statement 3? True, because yeah, so yeah, can you give an example? Right, so you can take a cycle of length n. So let's say you have this cycle, then all you do is you just travel across the edges, and you are visiting every edge exactly once, and you are visiting every vertex exactly once except the start vertex. So yeah, so this is Hamiltonian and Eulerian. So the answer is only statement B is true, because for the rest of them we have a counter example. Sorry. So now, just to connect with this discussion that we had, where we defined the decision problem, and now I'm going to change the problem to, instead of Eulerian, I'll say yeah, I'll say that I'll give you a graph as an input, and you have to check whether the graph is Hamiltonian or not. If yes, then yeah, then that should be your output. So output is just yes or no. So do you think this problem would be easy? um, yeah, Ojas, yeah, feel free to leave. Yeah, sure, thanks for attending. So yeah, so do you think you can have a easy algorithm for, I mean, efficient algorithm for this? So what would be a brute force sort of approach? What would be the most um, I mean, very trivial algorithm that you can think of? Okay, so let me discuss one approach. So you want to check testing Hamiltonian. Okay, so what you can do is, uh, you first choose your starting vertex. There are n possible vertices that you can have. After that, you choose the next possible vertex out of the n vertices. and so on. So notice that if you have a Hamiltonian tour, it has to be of length n, because once you visited this vertex, you cannot ever come back to it. So each vertex is going to be visited exactly once except the starting vertex. Therefore, it has to be of length n. So what you're doing is you're just guessing a path of length n. There is an n length path, and you're just checking which vertex will be here, which vertex to visit here, and each of them has n choices. That's the most brute force thing I'm doing. So each of them has n choices, so totally there are n to the n, which is like 2 to the n log n, many yeah, this would be the running time, which is very very bad for us, like we mentioned here. And it turns out that this problem is hard in the sense you do not know an algorithm for this which is better than exponential or something. So this Hamiltonian path, Hamiltonian testing problem is a hard problem. And by hard, we don't mean that you can never do better. By hard, we mean we do not know anything better. So I mean, I just wanted to mention that there are these two problems which are very similar, where instead of edges you are just talking about vertices. That's the only difference. And suddenly there is a huge difference in the difficulty of the problem. So there is a whole area in complexity which deals with hardness of problems and classifying them based on their hardness. But we're not going to deal with that in this course. But I just wanted to mention, since the topic came up, I just wanted to let you know regarding the complexity aspect of it. So yeah, if it does not make sense, that is totally fine. But yeah, I just wanted to mention it. Okay, so you can try this question about Hamiltonian cycle. So what do you mean by Hamiltonian cycle? It's just that you start at the same vertex, go back to the same vertex, and visit every other vertex exactly once. So you have this graph which has 9 vertices, and it's a 5 regular graph, meaning every vertex has a degree of 5. So the question is, does it have a Hamiltonian cycle? Okay, Akansha says yes. So, um, okay, so that the answer is indeed correct. So, what you do is, you can either use the idea of the degree sequence thing that we saw last time. So you have this sequence to start with, and this is 9 times, and you can keep on um, doing the degree changing business, where you make the star and remove 1 degree, reduce 1 degree, and so on. So if you follow these steps, you will end up getting a you will get end up getting a graph with all the edges and so on. And then you can check if there is a cycle. That is one thing to do. Or what you could do is you can use this theorem, which is called Dirac's theorem, which says that um, if every vertex in G has degree greater than n by 2, then it has a Hamiltonian cycle. So in this case, n is 9, so and the degree of each vertex is 5, which is clearly more than 9/2. Therefore this condition here is satisfied, and you get this, you can conclude that yes, the graph does have a Hamiltonian cycle. Now yeah, so now the question I want to ask you is, we just said that this problem is hard, right? We said we don't know anything better than this 2 to the n and something like exponential. And why can't we just use this Dirac's theorem and get a better algorithm? What is the problem with that? Exactly, good. So Akansha says that you, while you can tell if certain condition is true, then the graph is Hamiltonian, but the opposite direction is not true. So if there is a Hamiltonian cycle, then it's not necessary that this condition holds. So this is just a sufficient condition, but this is not a necessary condition. That's why it's not enough to tell your yes no answers. So this is just a necessary condition. Okay, good. Okay, so I'll first take these questions on chromatic number, and then we will do the planar related questions. So what do you mean by chromatic number of a graph? It's just that you have yeah. So what you're going to do is you're going to color the vertices of a graph. So for example, I have this graph, and what I'll do is I'll color this vertex with yellow, let's say. Now the way in which I'm going to color is that if this vertex is yellow, I can't color its neighbor with yellow because I want them to be distinguishable. So now I'm forced to color this guy with some other color. So let's say I color it with green. Now yeah, but now I can for example, now I can color this guy with yellow and this guy with yellow. I can't do with green, because if I do so, then again there are neighbors which have the same color, and then there would be neighbors which have the same color. And now let's say I color this one with blue. So I ended up using 3 colors in this case. So but I want to use as minimum colors as possible. So in this case, what I could do is I could just cleverly reuse the color. I could just reuse this green color here because this vertex does not have a green neighbor. Had there been this edge, this one more edge, then I would have needed more colors. But in this case, I don't need. So a chromatic number of a graph. So this kind of coloring is called a proper coloring, where you're going to color the vertices such that no two adjacent vertices have the same color. This is what a proper coloring means. And what is a chromatic number of a graph? A chromatic number is simply that the minimum number of colors needed to properly color a graph G. So in this case, the chromatic number of this graph is 2, because I can color it with 2 colors, but I can't color it with 1 color, because if I use yellow here again, then I'm violating the proper coloring condition. So that's what we mean by chromatic number. And the question is, you want to tell the chromatic number for this graph. So I'll just be back in a couple of minutes. In the meantime, please try this out. Hi, sorry. So, yeah, so the answer, yeah, you're right. The answer is 3. So, can you tell me the coloring that you have in mind? So, maybe tell me green, blue, yellow colors, maybe. Okay, so yeah, so let's try this out. So let's say you color this vertex A with yellow, then you can't color C with yellow because you have, yeah, you'll create a contradiction. So let's say I color this three with the three of them with green. Now I can always color this one with yellow. Sorry, is there a, yeah, you can't color this with, yeah, so you'll have to take a different color for this and a different color for this, because you have to take a color which is different from A and different from the color of E, because they both are adjacent to C. So this one ends up getting blue, and now you can either color this with green or blue. So in this case you could uh, you could show a coloring which with three colors, but does that mean the chromatic number is 3? You want to also show that you can't do with less than 3. So what would be an argument for that? So you want to show, so here is a coloring with 3 colors, but you want to show that there does not exist a proper coloring with 2 colors. Then how do you show that? So what you can do is you can look at this click here. So there is this particular subgraph where you have A is connected to C, C is connected to E, and E is also connected to A. So what you are saying is that let's say you color A with yellow, then you cannot color C with yellow, you cannot color E with yellow, because they are adjacent. Therefore you have to choose second color, which is say green for now. Now you can't color E with A and you can't color E with C, so you have to take another color which is E. So essentially you have a click here which is of size 3, therefore you need at least 2 colors, sorry, more than 2 colors. So this is a general argument, and you can generalize this idea. You can say that if there is a k click in the graph, then that implies that the chromatic number of that graph is at least k plus 1. So that's a general statement that you can prove using same ideas, or you can try to do it using induction. So I'll leave it there for now, and I'll move on to the next question. So yeah, so you're given some statements that first statement says that every cycle is 2 colorable. By 2 colorable we mean you can color it using 2 colors. And second statement is every bipartite graph is 2 colorable, and the third is every tree is 2 colorable. So you can try this out and let me know what you think. Okay, yeah, good, that is correct. So yeah, so do you have a counter example for statement 1? Yeah, good. So a cycle of length 5, or any cycle of odd length for that matter. So if you have say a cycle of length 5, and say you color this one with yellow, then you're forced to color the neighbors with a different color. And sorry, what is what is sorry what is wrong with this? Okay. So now you color this with yellow, but you can't color this vertex here with either yellow or green because both are neighbors. So you are forced to choose a different color, which is this. So right. Um, yeah. So for first statement is clearly false. What about statement 2? So statement 2 says that every bipartite graph is two colorable. So what you can do is think of these as your two partitions because it's a bipartite graph, and you know that the edges are always going to be across these partitions. You can never have edges within the partitions. So what you can do is you can color all these vertices with yellow and all these vertices with green, because all the edges are anyway going from a yellow colored vertex. I mean, all the edges are anyway between a yellow colored vertex to a green colored vertex. You cannot ever have yellow to yellow edge, or you cannot have green to green edge. Hence it's just sufficient to do these two colors and get a valid two coloring. So therefore, if you have a bipartite graph, then it is indeed two colorable. And um so okay, so I'll just pose this question. So you're saying here that bipartite implies two colorable. What about the other way around? Is it true that um, true that if you have a two colorable graph, then it is bipartite? Yes. So the idea is again, yeah, the idea is again similar. So if you have two colorable graph, then what you do is you take all the, and let's say I'm coloring it with yellow and green. So what you do is you take all the yellow colored vertices and collect all the green colored vertices on one side, and then you think of these, sorry, then you think of these yellow colored vertices as your partition A and the green colored vertices as your partition B, and then you know that the edges are anywhere across them, because otherwise it would not have been a two colorable graph if there were an edge between yellow colored or green colored amongst themselves. So it's the same idea but in the opposite direction. So it's in fact an if and only if statement. um yeah. So in order to show statement 3, sorry, this is 3. In order to show statement 3, it's sufficient to show that a tree is bipartite. So then you can just use statement 2. So suffices to show statement uh, suffices to show that a tree is bipartite. If you can show this, then by statement 2 you know that a bipartite graph is two colorable, and therefore tree is two colorable. So okay, in fact this is not even needed. You can also directly you can also directly give the two coloring of tree. I think that is easier, I think. Yeah. So this is what your tree would look like. You have different levels. So you have level 1 where there is root, then there are children of the root, then there are children of the root, and so on. So this is what it would look like. And what you do is you, let's say, color this one with yellow, then in the next level you color all of them with green, then you color the rest of them with yellow, and you keep on repeating. Essentially you alternate between the colors, and you would never end up getting yeah, you would never end up getting edges that go within the same partition, and the same argument would essentially show that the graph is also bipartite. So the answer um, is statement 2 and 3. Okay. So yeah, so you can maybe, yeah, you can try this out. I think I'll have to wind up early today, so this is this is maybe the last question that I'll take up for now, and yeah, I'll wind up for today. So you have a graph with 12 vertices and 6 faces, and you want to tell the number of edges in the graph. Okay, so what you do is you use this formula, Euler's formula, which says that, which you might have seen earlier. So it says that number of faces plus number of vertices is edges plus 2. So essentially you look at the number of, or maybe I'll just maybe take an example. So say this is an example where you have n is equal to 5, the number of edges is 6, and the number of faces is one here, one here, one here, and the one which is outer. So you have 4 faces here, and notice that if you add up the number of faces and number of vertices, then in this case okay. Sorry, the number of sorry, the number of edges here is 7, right? Yeah. So notice that if you add the number of vertices and faces, then you get 4 plus 5, which is 9, which is equal to m plus 2, which is 7 plus 2. It turns out this is what is called Euler's formula, which gives you this relation in general. So, and you can observe this for graphs as well. I think the proof of this is also not too hard to see, and I think it's probably done in the lectures. I'm not sure though. So I'm the point of this exercise is just to use the formula. So the number of regions or phases here is 6, the number of vertices is 12, and that is equal to the number of edges plus 2. So this gives you that number of edges is 16. Okay, so maybe in the next tutorial we will do more examples of this kind, but yeah, I have some constraints right now, so I'll have to wind up for today. So next we will meet on the coming Friday, which is 20th September. Sorry, same time, 6 p.m. to 8 p.m.